Hello students, in previous class we discussed about Mendeleev periodic table, silent features and achievements of the Mendeleev periodic table. Today in this class we are discussing about limitations of Mendeleev periodic table. So today now we are discussing limitations of Mendeleev periodic table. Anomalous pairs of element. First one, anomalous pair of element. Certain elements of highest atomic weight precedes those with lower atomic weight. For example, tellurium atomic weight is 127.6. This placed before the iodine. This iodine atomic weight is 126.9. Means here Mendeleev he placed the more atomic weight elements before the less atomic weight elements. So actually the Mendeleev he arranged the elements in the increasing order of their atomic weight, but when we observe the Mendeleev periodic table, in that we can observe more atomic weight element tellurium. Tellurium atomic weight is 127.6 and iodine atomic weight is 126.9. So this tellurium is placed before the iodium. Actually this iodine atomic weight is less when we compare with the tellurium. Okay, this is one of the limitation. Next, dissimilar elements placed together. Dissimilar elements placed together. Elements with dissimilar properties were placed in same group as subgroup A and subgroup B. Okay, so elements with dissimilar properties were placed in the same group as a subgroup A and B. For example, alkali metals like lithium, sodium, potassium, etc. of first A group have little resemblance with the kinase metals like copper, silver, iron of first group. Elements with dissimilar properties were placed in same group has subgroups A and subgroup B. Means we placed that elements with similar chemical properties are placed in the same group, he said. But when we observe subgroup A and B, that elements with different properties are placed in that. For example, alkali metals like lithium, sodium, potassium, okay, of first A group that have little resemblance with kinase metals like copper, silver, gold of first B. Okay, so Mendeleev said I placed the elements with similar copper properties in same group, he said, but first A group metals, okay, like lithium, sodium, potassium, that have some similar properties when we compare with the first B group with first B group of elements copper, silver, iron. Okay, next chlorine is of 7th A group and manganese of 7th B group. 7th B group. Okay, chlorine is belong to 7th A group, but manganese belongs to 7th B group. But chlorine is a non-metal, whereas manganese is a metal. Okay, actually Mendeleev said that I placed the elements with similar chemical properties are in the same group. Chlorine is belongs to 7th A group and manganese belongs to 7th B group. But chlorine is a non-metal, manganese is a metal. Metals properties, non-metals properties are different. Chlorine is a non-metal and manganese is a metal. So dissimilar elements placed together means he said that I arranged the elements which have similar properties in same group, he said, but when we compare with subgroups, okay, like 7th A and 7th B, means chlorine is belongs to 7th A group and manganese is belongs to 7th B group. This chlorine is a non-metal and manganese is a metal, but metal and non-metal properties are different, means different elements are placed in the subgroups. Okay, so this is one of the limitation. Anomalous is also one of the limitation in the Mendeleev periodic table. Now we will discuss about modern periodic table. H.J. Moseley in 1913 found that each element emits a characteristic pattern of X-rays when subjected to bombardment by high energy electrons. By analyzing the X-ray pattern, Moseley was able to calculate the number of positive charges in the atoms of respective elements. The number of positive charges means protons in the atom of an element is called as atomic number of that elements. So H.J. Moseley in 1913 found that each element emits a characteristic pattern of X-rays when they are subjected to bombarded by high energy of electrons. Okay, so when the element is subjected to high energy electrons, it is releasing, it emits the pattern of X-rays. By analyzing the X-ray pattern, Mosley was able to calculate the number of positive charges in the atom of respective elements. By observing that X-ray pattern, Mosley is able to calculate the number of positive charges in the atom of the elements. Okay, so the number of positive charges means protons only, no? So the number of positive charges means protons in the atom of an element is called as atomic number of the elements. With this analysis, Mosley realized that the atomic number is more fundamental characteristic of an element than its atomic weight. Okay, so by observing this X-ray pattern, Mosley is calculate the positive charges in number of positive charges in an element. Okay, by this number of positive charges means protons, that number of protons only called as atomic number of an element. Okay, after this, Mosley realized that the atomic number is the more fundamental characteristic of an element than atomic weight. Means Mendeleev he classified the elements by depending on the atomic weight. Means Mendeleev arranged the elements in the increasing order of their atomic weight, but in that some limitations are there. What are that? Means like anomalous series. Actually Mendeleev arranged the elements in the increasing order of their atomic weight, no? So but in that one limitation, what is that? Means anomalous series. Tellurium, it had more atomic weight, but it is placed before the less atomic weight. Means tellurium is placed before the iodine. Actually tellurium atomic weight is more, iodine atomic weight is less. Like that some limitations are there. So if we arrange the elements in the increasing order of their atomic number, then this type of problems we can overcome. Okay, so if we arrange the elements in the increasing order of their atomic number, then this Mendeleev we can overcome the limitation of Mendeleev. Okay, so atomic number means nothing but number of protons. So after knowing the atomic number of elements, it was recognized that a better way to arrange the elements in the periodic table according to their increasing order of their atomic number. So after knowing the atomic number of an elements, so they believed that it is better to arrange the elements in the periodic table in the increasing order of their atomic number. So this arrangement eliminate the problem of anomalous series. Okay, this arrangement is eliminate the problem of anomalous series. Okay, for example, tellurium, it has more atomic weight than iodine. Yes, yes or no? Yes. Okay, it has atomic number less by 1 unit when we compare it to iodine. Okay, so this atomic number concept was forced the periodic law to be changed. So here the atomic number of tellurium is 52 and atomic number of iodine is 53. Atomic number of tellurium is 52, atomic number of iodine is 53. So if we arrange the elements in the increasing if we arrange the elements in the periodic table in the increasing order of their atomic number, this arrangement eliminate the problem of anomalous series. Okay, so why? Because tellurium atomic number is there, no, that is less by 1 unit when we compare it to iodine. Okay, so this atomic number concept forced the periodic law to be changed. So after that, the periodic law is changed from atomic weight concept to atomic number concept, and now it is called as modern periodic law. Okay, so if Mendeleev arrange the elements in the increasing order of their atomic weight, then anomalous series, that type of problems will come. Means more atomic weight elements that will come before the less atomic weight, like tellurium and iodine. Okay, so mostly mostly he bombarded the element with high energy of electron, then that is emit the characteristic pattern of X-rays. By studying the X-ray pattern, Mosley is able to calculate the number of positive charges, means number protons. Okay, that by analyzing the X-ray pattern, Mosley was able to calculate the number of positive charges in the atom. of the respective elements. The number of positive charges of an element is called as atomic number of an element. Okay, so with this analysis, Moseley realized that it is better to arrange the elements in the periodic table in the increasing order of their atomic number, he said. Okay, so if we are this arrangement eliminate the problem of anomalous series. Okay, so after that this periodic law is Mendeleev periodic law. What is that? What is the Mendeleev periodic law? Mendeleev periodic law, this law states that physical and chemical properties of elements are the periodic functions of their atomic weight. But after the discovery of this atomic number concept, the periodic law changed from atomic weight concept to atomic number concept. Now it is called as modern periodic law. Okay, so the periodic law, it is changed from atomic weight concept to atomic number concept. So it is called as modern periodic law. Okay, if we change the periodic law like this, then that is eliminate the problem of anomalous series. We know that Mendeleev periodic law is stated as the properties of elements are the periodic functions of their atomic weight. Now let us try to understand the modern periodic law. What is that modern periodic law? The modern periodic law may be stated as the properties of the elements are the periodic functions of their atomic number. Okay, this modern periodic law is changed from atomic weight concept to atomic number. So the modern periodic law may be stated as the properties of elements are the periodic functions of their atomic number. So based on the modern periodic law, the modern periodic table which is given here is proposed. Okay, based on the modern periodic law, the modern periodic table which is given is proposed. Okay, it is the extension of the original Mendeleev periodic table. Okay, and known as short form of the table, and this modern table is called the long form of the periodic table. Okay, so based on the modern periodic law, the modern periodic table is which is given here is proposed. It is the extension of the original Mendeleev periodic table and known as short form of the table, and this modern table is called the long form of the periodic table. It is given in this figure, and atomic number of an element Z. Okay, atomic number of an element is showed by Z. This indicates not only the positive charges, means protons in the nucleus of an atom of the element, but also it represents the number of the electrons in the neutral atom of the element. Okay, so this modern periodic table is depending on the atomic number concept. Atomic number means number of protons. Okay, number of proton means number of positive charges. Okay, so this atomic number is indicates not only the positive charges which is present in the nucleus, it is indicates the number of electrons present in the element also. Okay, so the physical and chemical properties of atom of the element is depend on the number of protons, but on the number of electrons and their arrangement in an atom. Okay, so here atomic number means not only protons, we can say the number of electrons also. So the physical and chemical properties of elements is depend not only on the protons but also depend on the number of electrons also, and arrangement of electronic configuration in the atoms also. Therefore, the modern periodic law may be stated as the physical and chemical properties of elements are the periodic functions of the electronic configuration of their atoms. Okay, now we can say the modern periodic law like this: the physical and chemical properties of elements are the periodic functions of their electronic configuration of their atoms. Now we will discuss about the position of elements in the modern periodic table. Okay, so now we are discussing about the position of elements in the modern periodic table. The modern periodic table has 18 vertical columns known as groups and 7 horizontal rows known as periods. Okay, so the modern periodic table, it has 18 vertical columns. These vertical columns are known as groups, and 7 horizontal rows, these are known as periods. Let us see what decide the position of an element in the periodic table. So now we will see what decide the position of a element in the periodic table. Okay, we can explain the classification of elements in the modern periodic table in terms of certain electrons arrangements which are periodically repeated. So the element with a similar outer shell electronic configuration in their atoms are in the same column is called as groups. Elements listed in a group down to it are in the order of their increasing principal quantum number. Okay, so we can explain the classification of elements in the modern periodic table in terms of certain electron arrangement which are periodically repeated. Okay, so the element with a similar outer shell means valency shell electronic configuration in their atoms are in the same column is called as group. Okay, elements listed in a group down to it are in the order of their increasing principal quantum number. Okay, so means the element which have outer shell configuration is same, that will be arranged in same group. Okay, so once you observe the first group, hydrogen atomic number 1, its configuration 1s1, lithium atomic number 3. Okay, and its configuration 1s2 2s1, sodium its atomic number 11, its configuration 1s2 2s2 2p6 3s1, like that. And potassium, it is atomic number 19, its configuration 1s2 2s2 2p6 3s2 3p6 4s1. So if you observe this hydrogen, lithium, sodium, potassium, its configuration finally S1 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 like this coming or not? Finally S1 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 it is coming like this, but its principal quantum number is changing, means hydrogen 1s1 1 it is. Okay, means it is belongs to first shell. Lithium 1s2 2s1 means 2, it's belong to second shell, like that. Okay, sodium 1s2 2s2 2p6 3s1 3 means it is belongs to third shell. Okay, potassium 1s2 2s2 2p6 3s2 3p6 4s1 4. Okay, its principal quantum number is increasing, but last, okay, outer shell configuration is same, like that, that is entering. Okay, so we can explain the classification of elements in the modern periodic table in terms of certain element arrangements which are periodically repeated. Means the elements with a similar outer shell means valency shell electronic configuration in their atoms are in the same column, it is called as groups. Okay, elements listed in a group down to it are in the in the order of their increasing principal quantum number. Okay, so in the chapter structure of atom, you have learned that S subshell with one orbital contain maximum 2 electrons. Okay, in structure of atom we learn S subshell, so that have one orbital and it contain 2 electrons, and each p subshell contain 3 orbitals and its accommodate maximum 6 electrons, and each d shell subshell that contain 5 orbital and that accommodate maximum 10 electrons, and F subshell it contains 7 orbitals and it accommodate 14 electrons. Depending upon to which the subshell the differentiating electron, that last coming electron entering into the atom of a given element, the element are classified into S, P, D and F black elements. Means here S subshell it accommodate 2 electrons, P subshell it accommodate 6 electrons, D subshell it accommodate 10 electrons, F subshell it accommodate 14 electrons. Okay, so here if the atomic number increasing, then the electrons are entering into different orbitals. So by depending on the entering of the electrons into orbitals, okay, that's so here some electrons are entering into hydrogen is there, it's atomic number 1, configuration 1s1. Okay, means it belongs to S black element, like that we can say. Okay, so next carbon is there, its atomic number 6. Okay, its configuration 1s2 2s2 2p2 means its last electron entering into p orbital, no, means that's why we can say it belongs to p black element. Okay, like that. So depending upon to the which subshell the differentiating electrons in the last coming electrons enters into an atom of the given element, the element is classified into S, P, D, F. Means last electron entering into which orbital, by depending on that we can classify the elements belongs to S, P, D, F black element. For example, sodium, it gets new Na, okay, it's a new coming electron entering into 3s level. Okay, in sodium, last electron entering into 3s level, no. So therefore Na is belongs to S black element. So like that, aluminium, okay, aluminium gets its differentiating electron into p subshell. In aluminium, aluminum electronic configuration 1s2, 2s2, 2p6, 3s2, 3p1. Okay, aluminum atomic number 13, its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p1. Last electron entering into p orbital, no, that's why we can call that as a p black element. Scandium, its atomic number 21. It's a configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Last electron entering into d orbital, no, that's why we can call this as a d black element. Okay, next cerium, its atomic number 58. Its configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 6s2, 4f2. Means last electron entering into f orbital, no? Then we can call that as a f black element. Okay, like this, the last electron entering into which orbital, by depending on that we can classify the elements as a s black element, p black element, d black element, or f black element. Okay, now we will discuss